So that tells us that dA prime, the area element in UV coordinates, is worth 5 times more than the area element in XY coordinates. So that means du dv is worth 5 times dx dy. What's so funny? What? Oh. Okay, rectangle. Okay, is it okay now? Or did I misspell other words? No? Okay. It's really hard to see when you're that close up. It's much easier from a distance. Okay. So we've said our transformation multiplies areas by 5. And so du dv is 5 times dx dy. So if I'm integrating some function dx dy, then when I switch to UV coordinates, I will have to replace that by 1/5 du dv. Okay? And of course, I would also, here my function would probably involve x and y. I will replace them by u's and v's. And the bounds, well, the shape of my region in the xy coordinates, I will have to switch to some shape in the UV coordinates. And that's also something that might be easy or might be tricky depending on what region we're looking at. So usually we'll do changes of variables to actually simplify the region, so that it becomes easier to set up the bounds. So anyway, so this is kind of an illustration of a general case. And why is that? Well, here it looks very easy. We're just using linear formulas, and somehow the relation between dx dy and du dv is the same everywhere. If you take actually more complicated changes of variables, that's not true, because usually you will expect that there's some places where the rescaling is maybe enlarging things, and some other places where things are shrunk. So certainly the exchange rate between du dv and dx dy will fluctuate from point to point. It's the same as if you're trying to change dollars to euros. It depends on where you do it. You will get a better rate or a worse one. We have to, of course, we'll get a formula where actually the scaling factor will depend on x and y or on u and v. But if you fix a point, then we have linear approximation. And linear approximation tells us, we can do as if our function is just a linear function of x and y. So then we can do it the same way we did here. Okay, so let's try to think about that. So in the general case, well, that means, we'll replace x and y by new coordinates, u and v. And u and v will be some functions of x and y. So, well, we'll have an approximation formula which tells us that the change in u, if I change x or y a little bit, will be roughly u sub x times change in x plus u sub y times change in y. And the change in v will be roughly v sub x delta x plus v sub y delta y. Or the other way to say it, if you want in matrix form, is delta u delta v is approximately equal to u sub x u sub y v sub x v sub y times delta x and delta y. Okay? So if we look at that, what it tells us, in fact, is that if we take a small rectangle in xy coordinates, so that means we have a certain point xy, and then we have a certain width. Oh, this is going to be too small. Need a So I have my width delta x, I have my height delta y. This is going to correspond to a small UV parallelogram. And what the shape and the size of that parallelogram are depend on the partial derivatives of u and v. So in particular, they depend on at which point we are. But still, at a given point, it's a bit like that. And so if we do the same argument as before, what we'll see is that the scaling factor is actually the determinant of this transformation. So that's one thing that maybe we didn't emphasize enough when we did matrices at the beginning of the semester. But when you have a linear transformation between variables, the determinant of that transformation represents how it scales areas. Okay, so one way to think about it is just to try and see what happens. Take this side. This side in xy coordinates corresponds to delta x and 0. And now if you take the image of that, if you see what happens to delta u and delta v, that will be basically u sub x delta x and v sub x delta x. There's no delta y. For the other side, okay, so maybe I should do it actually. So, if we move in the xy coordinates by delta x and 0, then delta u and delta v will be u sub x, so it will be approximately u sub x delta x and v sub x delta x. And on the other hand, if you move in the other direction, along the other side of your rectangle, 0 and delta y, then the change in u and the change in v will correspond to, well, how does u change? That's u sub y delta y, and v changes by v sub y delta y. And so now if you take the determinant of these two vectors, okay, so these are the sides of your parallelogram up here, and if you take these sides to get the area of the parallelogram, you would need to take the determinant. And the determinant will be the determinant of this matrix times delta x times delta y. So the area in UV coordinates will be the determinant of the matrix times delta x delta y. And so what I'm trying to say is that when you have a general change of variables, du dv versus dx dy is given by the determinant of this matrix of partial derivatives.